You want to know what happens if a black hole fights the Earth? That's not the right question, because a black hole doesn't fight, it doesn't attack, it doesn't do anything. A black hole just sits there, and everything else falls into it. Let me tell you what would actually happen. And I'm warning you now, this isn't going to be a fair fight. This isn't even close. This is like asking what happens if you drop an ant into a wood chipper. The ant doesn't stand a chance. Neither does the Earth. But let's be precise about this. Let's actually work through what happens step by step, because the details matter, and the details are absolutely horrifying. First question. What kind of black hole are we talking about? Black holes come in different sizes. Small ones, stellar mass black holes, form from collapsed stars, about 3 to 20 times the mass of the Sun. Medium ones, intermediate mass, hundreds or thousands of solar masses, and supermassive ones, sitting at the centers of galaxies, millions or billions of times the mass of the Sun. The size matters because it determines how close you have to get before things get really bad. A black hole has something called the event horizon. That's the point of no return. Cross that boundary and you're done. Nothing, not even light, can escape from inside the event horizon. That's what makes it black. For a black hole with the mass of the Sun, the event horizon is about 3 kilometers across. For a supermassive black hole with 1 billion solar masses, the event horizon is about the size of our solar system. Bigger mass, bigger event horizon. The radius scales linearly with mass. So let's start with a small one. A stellar mass black hole. Let's say 10 times the mass of the Sun. Event horizon about 30 kilometers across. That's tiny. Manhattan is bigger than that. Now, let's bring this black hole toward Earth. What happens? Nothing. Not at first. When the black hole is far away, millions of kilometers out, nothing changes. The Earth keeps orbiting the Sun. The Moon keeps orbiting the Earth. Life goes on. Because gravity obeys an inverse square law. The force gets weaker with distance. Far away, even a black hole's gravity is negligible. But as it gets closer, things start to change. Let's say the black hole is now 1 million kilometers away. That's about 3 times the distance to the Moon. Still far, but now you can start to feel it. Not you personally. You're too small, but the Earth feels it. The oceans feel it. Tides start to shift. Water starts bulging toward the black hole. Not much, just a little. But it's there. The black hole keeps coming. Now it's 100,000 kilometers away. The tides are stronger. The oceans are sloshing. Earthquakes are starting. The Earth's crust is flexing under the gravitational strain. People are noticing. This is bad. 50,000 kilometers. The Moon's orbit is getting disrupted. If the black hole passes close to the Moon's trajectory changes. Maybe it gets flung away into space. Maybe it falls toward the black hole. Either way, the Moon is gone. 10,000 kilometers. Now it's serious. The Earth is being pulled. Hard. The side of the Earth facing the black hole is being pulled more strongly than the center. And the center is being pulled more strongly than the far side. This is called a tidal force, and it's tearing the Earth apart. The atmosphere starts getting ripped off. Air rushes toward the black hole. The oceans follow. Water evaporates into space. The crust cracks. Volcanoes erupt everywhere. The surface of the planet is disintegrating. 1,000 kilometers. The Earth is stretching. The planet is no longer spherical. It's becoming egg-shaped, elongated toward the black hole. The tidal forces are enormous. The entire planet is being pulled into a long, thin stream. This process has a name, spaghettification. I'm not joking. That's the actual term astronomers use. The Earth is being turned into spaghetti. Rocks, water, air, everything, stretched into long, thin strands, spiraling toward the black hole. The planet doesn't exist anymore. There's no more Earth. Just a stream of matter falling inward. And here's the thing. This happens fast. Once the tidal forces get strong enough to overcome the Earth's structural integrity, it's over in minutes. Maybe less. The Earth doesn't slowly erode. It doesn't gradually break apart. It gets shredded violently. catastrophically, instantly. Now let's talk about what happens to that stream of matter as it falls in. When something falls toward a black hole, it doesn't just drop straight in. It spirals. Because the black hole is rotating, or because the infalling matter has some sideways motion. Either way, it forms what's called an accretion disk, a swirling disk of material orbiting the black hole before falling in. And here's where things get really interesting. That disk gets hot, incredibly hot. Why? Friction. The material in the disk is rubbing against itself. Inner parts are moving faster than outer parts. That creates friction. And friction generates heat, enormous amounts of heat. How hot? Millions of degrees. Hot enough that the material starts glowing. First red, then orange, then white, then blue, then ultraviolet, then X-rays. The accretion disk around a black hole is one of the brightest things in the universe. It outshines entire galaxies. So here's the irony. A black hole is black. Light can't escape from inside the event horizon, but the area just outside the black hole, the accretion disk, is blindingly bright, brighter than anything else you can imagine. If you were watching from a safe distance far away, you wouldn't see the Earth getting eaten by darkness. You'd see it get torn apart and then incinerated in a blaze of light so intense it would vaporize anything nearby. Now let's follow a piece of the Earth as it falls in. Let's say a chunk of rock, maybe a cubic meter. It's in the accretion disk now, spiraling inward, heating up, glowing white hot. It's moving faster and faster as it gets closer to the event horizon. Orbital speeds near a black hole approach the speed of light. The rock crosses the event horizon. What happens? From the outside, from your perspective watching from far away, the rock appears to slow down. As it gets closer to the event horizon, time dilation kicks in. Clocks near a black hole run slower than clocks far away. This is general relativity. Gravity warps time. The rock appears to freeze at the event horizon. It gets redder and dimmer as the light coming from it gets stretched to longer and longer wavelengths. Eventually, it fades from view. It looks like the rock never actually crossed the horizon. It just stopped there, frozen in time. But that's just how it looks from the outside, from the rock's perspective. From the perspective of someone riding that rock, something very different happens. The rock doesn't slow down. It doesn't stop. It crosses the event horizon and keeps falling. And from its perspective, nothing special happens at the horizon. There's no barrier, no wall, no sensation. You just pass through. If you were falling in, you wouldn't even notice the moment you crossed the point of no return. But then things get bad. Inside the event horizon, the tidal forces get stronger, much stronger. If the black hole is small, stellar mass, the tidal forces are so strong that they tear the rock apart. Then they tear the atoms apart. Then they tear the protons and neutrons apart. Everything gets crushed and shredded down to fundamental particles, and it all falls toward the center, toward the singularity. That's the point at the very center of the black hole where all the mass is concentrated, where the density becomes infinite, where the equations of general relativity break down and stop making sense. We don't know what happens at the singularity. The math says infinite density, infinite curvature of space-time, but infinity in physics usually means we're missing something. Maybe quantum mechanics changes the picture. Maybe there's no actual singularity. Maybe it's something else entirely. We don't know. Nobody knows. But here's what we do know. Once you cross the event horizon, you can't get out. Not ever. Not by any means. Inside the horizon, all paths lead to the singularity. You can't escape. You can't even try. The geometry of space-time itself forces you inward. It's not that the black hole is pulling you. It's that space itself is falling inward faster than light. And since you can't go faster than light, you can't swim upstream against the flow of space. You're trapped. So that's what happens to the Earth. It gets torn apart by tidal forces. The pieces spiral into an accretion disk. They heat up to millions of degrees. They glow brighter than stars. They cross the event horizon. They fall to the singularity. And they're gone. Forever. The Earth loses. Badly. But wait. Let's change the scenario. What if it's a supermassive black hole? One with 1 billion times the mass of the Sun? Now things are different. Bigger black holes have weaker tidal forces near the event horizon. That sounds wrong, but it's true. The tidal force depends on how quickly gravity changes with distance. For a small black hole, the event horizon is tiny, and gravity changes very rapidly over short distances. For a supermassive black hole, the event horizon is huge, and gravity changes much more gently. So if the Earth fell toward a supermassive black hole, it wouldn't get spaghettified as early. It might actually make it to the event horizon more or less intact. The planet would cross the horizon in one piece. But that doesn't save it. Once inside, it still falls to the singularity. It still gets destroyed. It just happens later, deeper inside. And here's the really weird part. For a supermassive black hole, you could fall through the event horizon and not notice. If you were on the Earth as it crossed, you wouldn't feel anything unusual. You'd look around and everything would seem normal. The sky, the ground, the air, all normal. You wouldn't know you'd crossed the point of no return. You'd only realize something was wrong when you looked up and saw that the stars behind you had vanished. Because light from outside can fall in, but light from inside can't get out. So the view behind you would go black. And the view ahead would get brighter and brighter as you fell deeper in. And then, eventually, the tidal forces would kick in. Even for a supermassive black hole, once you get close enough to the singularity, the tidal forces become infinite. You'd be stretched and compressed and torn apart. It would just happen later than with a small black hole. So in either case, the Earth loses. The black hole wins. Every time. No contest. But let's ask a different question. Could the Earth ever destroy a black hole? No. Black holes don't die. Well, technically they do. Stephen Hawking figured out that black holes emit radiation due to quantum effects near the event horizon. Hawking radiation. This causes black holes to slowly lose mass over time. Eventually, they evaporate completely. But the timescale is absurd. For a black hole with the mass of the Sun, it would take 10 to the 67 years to evaporate. That's a trillion years. The universe is only 14 billion years old. For a supermassive black hole, it's even longer. So in any practical sense, black holes don't die. They're essentially immortal, and nothing you do to them makes them weaker. In fact, the opposite. Every bit of matter that falls in makes them stronger, bigger, more massive. If you throw the Earth at a black hole, the black hole just gets slightly heavier. It doesn't slow down. It doesn't get damaged. It just eats the Earth and gets a tiny bit bigger. So who would win in a fight between a black hole and the Earth? The black hole. By an absurd margin. The Earth gets ripped apart, incinerated, and consumed. The black hole doesn't even notice. But here's the beautiful part. Here's what you should really take away from this. Black holes are not monsters. They're not evil. They don't hunt. They don't attack. They're just regions of space-time where gravity is so strong that the escape velocity exceeds the speed of light. That's all they are. Everything that happens, the spaghettification, the accretion disk, the event horizon, the singularity, all of it is just gravity. Pure, simple, predictable gravity. Einstein's equations describe it perfectly. We can calculate exactly what happens. We understand it. And that understanding is more incredible than any fight. Because what it tells us is that space and time themselves can be bent, twisted, and torn. That matter can be compressed to infinite density. That the universe contains regions where the normal rules break down and something stranger takes over. Black holes are not the universe fighting the Earth. Black holes are the universe showing us what it's capable of, showing us how extreme reality can get, showing us that the laws of physics, pushed to their limits, produce things so bizarre, so extreme, so utterly alien that they defy imagination. The Earth doesn't stand a chance. But that's not a tragedy. That's just physics. Cold, precise, beautiful physics. And that's the real answer. Who would win? Physics. Physics always wins.